Let's look at a problem called 3SUM. And in this problem, we're given an unsorted array. We return all of the arrays containing 3 items that sum to 0, coming from the original array. So -1, 0, and 1, they come from the original array. -1, -1, 2, from the original array. Both of these arrays sum to 0 individually. We're not guaranteed that these arrays are sorted. So first off, I want to point out that we're guaranteed these are integer arrays. And whenever we have integer arrays, we can use radix sort or we can use bucket sort to sort these arrays in linear time. And normally we say that comparison sorting algorithms have a lower bound of n log n, and that's true. But those are for general sorting algorithms where you don't know what kind of input we're going to have. But in this case, we know it's integers, so we can use our sorting algorithms that operate on numerical values like that. So that's our first insight. We can sort this. We're given it unsorted, and we can solve this without sorting it. So let's solve it without sorting it first. And I want you to be introduced to another problem, reduction. If we can find the sum for 3 numbers, why can't we find the sum for 2 numbers? And this is going to factor into how we solve this, and it also will factor into how we could solve for sum, or arbitrary number of sums. But we're just going to stick to 2 and 3 for now. So how would we find 2 items that sum to 0 in this array? All right, here's our array. And if we wanted to do this exhaustively, we could find all pairs of items. How many pairs are there going to be? Well, 1 is going to pair itself with everyone else. And then 0 is going to pair itself with everyone but itself. 1 will pair itself with everyone. 2 will pair itself with everyone. So for n items, we're going to pair up with the n-1 other items. So ultimately what happens is we have an upper bound of n squared work going on. Because if we check all of these pairings to see if they go to 0, because now remember we're going for a 2SUM that solves to 0, that's going to be way too much work. And ultimately what we really care about is we care whether a previous item that has been seen, I use it to bring the sum to 0. And the way that we can often improve the time complexity of recomputations is with a hash table. We're going to get into all of this in the hash table section, but hash tables are one of our largest, most important structures when it comes to preventing repeated passes over data that we have already seen. If we've already seen data, there's a 99% chance that we can use a hash table to keep some sort of metadata to prevent recomputation and reiteration. One thing we can do is, if I'm at -1, all I care about is what have I seen before, and what do I want to have seen. If I'm -1, I wish there was a 1 that could bring the sum to 0. If I'm at 2, I wish there was a -2 somewhere that can bring the sum to 0. If I'm at 4, I wish there was a -4 that could bring the sum to 0. Well, we can use a hash table to remember the index that each of these values occur at. And we want to find the complement from any position, and then we'll know what index it's at. So we can create a hash table mapping complement to index. So just follow me. We're going to do a for loop. And what happens is we're going to say -1. Who can I find as my complement? This table's empty, so we can't find a complement yet. Someone later might be able to complement us, but for now, we're going to store -1 into the hash table, and we're going to store the index as 0. And then we can go to the 0, and we can say, who can I sum with to bring myself to 0? Well, I would want to find another 0, and maybe in some cases 0 couldn't be a number in this array, but let's just imagine it has to be a pair, so there has to be another 0. So there's nothing we can do here because there's no entry in the table that can complement the 0, and ultimately we just add 0 to the table and notate its index. We come to the 1, and then we say, hey, is there a guy that can complement me? We do 0 minus 1, which if we were to find a complement, it would be the opposite of 1. That means we look up -1 in the hash table. Did I find a -1 earlier? Yes, I did find a -1 earlier. So that's great. We could just return this pair and say we found a 2SUM. We also can just keep going and just continue this iteration just to get the feel for what we're doing here. So we're going to notate the 1 into the hash table and its index. And imagine our target sum was actually some other number, like 9. If I'm sitting at the 2, then what do I wish I had seen in the hash table? I wish I had seen a 7. So what we would do is we do target minus this item is what we wish we had seen previously. And then we would look that up in the table. And there's multiple ways you could do this, but this is the basic idea. Store either the complement or the actual number into the hash table, and when you're at future entries, look back. Now let's look at if the array was sorted. How would that pan out? How would we do this problem? If the array is sorted, things can change a bit. We can actually take another approach without using linear space with a hash table. This caching prevents us from recomputing and trying to find complements again by just remembering, hey, these are who can match up with you, but we can do something different with a sorted array. Now, if we have a sorted array, imagine our target is 11. We're going to be able to do a 2-pointer approach here. Because think about it, we're trying to mix up a concoction that will sum to this target sum. What is the best way to mix 2 items together to allow us to reduce our search space with us in control of changing the value? This array is sorted, so imagine if we take the smallest item and we take the largest item. Now I have the ability to trust that if I move that pointer inward, I'm going to get smaller values. If I move the left pointer this way, inward as well, I'm going to get greater values. If we take the sum right now, the sum is 10. What does that tell us? We undershot the target. We undershot the target of 11. That means we need more value. How do I get more value? I need to I can rely that I can move this pointer inward. And then we have a new sum. The new sum is 29. I now notice I overshot in value. I'm greater than my target. And this is literally almost like a binary search of sorts. It's just a search space reduction. You're going to see this in a problem like a 2D sorted matrix. When something's sorted, it gives us control over how we can manipulate these pointers to get what we want. We can slowly cook up and mix these together to get our target. You're going to see this in other problems. This is something to take away. So now reduce the right so that we can get less in value. So we hit 19, we overshot again, close the right boundary. Now we undershot with 5, close the left. And then this is 11. And once we hit 11, we either can close the right, we can close the left. It doesn't really matter because these hit the target sum. We can change it however we want, close in the left, and now they're overlapping, so end the iteration. So we would have either immediately returned or we would have added them to a list or however the caller would want us to handle this. But this is how we would deal with a sorted array. So how do we scale this to the problem of the 3-sum? How do we use the same strategy to find 3 items instead of 2 items? First off, we can get away with sorting this array. We don't have to. We can use the same hash table approach of complements to achieve the exact same thing we just did, but we can just keep this simpler and just sort it and use linear time with one of our integer sorts. And then that's going to give us this array. So we've sorted our original array, and we know how to find a 2-sum in linear time. What we just did was linear time. We're going to touch n elements doing constant work. How can we do the same thing for this array? We can do the same thing for this array by finding a 2-sum for every single element by rooting at elements and then finding a 2-sum within a search space. So with this problem reduction, we can actually do the same subroutine. It's just we have one more number in the mix. So this is what I mean. I say, I'm guaranteed that -4 is going to be in this triplet. And then I say, complement -4 with the rest of the search space. -4 is one of the numbers. This search space needs to nullify this -4. The target is to nullify this guy with whatever we can find in there. And then that is one iteration. Then the next iteration, we choose another root. We've already explored -4 as a number in one of these triplets. And there's no reason to have it in the search space anymore because all of the triplets that -4 could have existed in would have been discovered in that initial 2-sum nullification search, that search to nullify the -4. Now we say, hey, -1, you're guaranteed to be in the triplet. Can I complement you with anyone else? Can I nullify this to 0? To sum search. And then we do another rooting at this -1. And then notice how we're rooting at something that is the same as this -1. We can use a set. The code in the description uses a set. It's a bit slower than just using the iteration technique where you skip over items, but I thought it would be easier to understand with the set that maintains uniqueness of the items within the final results list. But in reality, we would want to skip over this and use a smarter iteration to skip over and not have to do this. But for simplicity's sake, let's just imagine we do root here and our set enforces uniqueness. Then we would find all the complements here, then we would continue. And going back to the set approach, remember it wouldn't change the asymptotic complexity, it would just change the real elapsed time. It's just going to change the wall time. It will not change how this algorithm reacts to really large inputs. Skipping duplicates will only save us a bit of work, but it won't change the fact we're touching n items and doing a linear time complement scan. So we root ourselves as 0 now, and then we try to find a complement of 2 numbers in this section, and we find out that if we continue our iteration, if we place the rooting here, it's impossible to find 2 numbers in the to_sum section we would search. So the search stops when we're right back here. Our last rooting happens right there. So the code in the description uses this set approach. Asymptotically, our time complexity is going to be n items. For each of these n items, we're going to be doing a linear time to_sum search. The to_sum's bounded to linear time. We're touching n items. Ultimately, our time complexity is big O of n squared. We upper bound to that, and then our space complexity, not including the output, is going to be constant because we are not creating any auxiliary structures that are going to store something that scales. Besides the output is going to have a certain size to itself. So that is how you can deal with the 2_sum, 3_sum problem, and this logic also scales to 4_sum. We would just root at all the elements and then find a 3_sum in the rest of the section. So remember, the hash table keeps our previous entries, can prevent us from doing additional passes over an array or structure that are dependent that will cause a high time complexity. And then also we noticed how we can reduce subproblems and then build them back up to solve the original problem. This is not divide and conquer. It's not dividing subproblems in that sense, just dividing problems into other problems that we already know how to solve that are simpler. So that is the 2_sum, 3_sum, and then you can scale this to the 4_sum problem.